So I'm very excited because I've got something very special. We're going to talk all things 9000 series launch, but also a bunch of the stuff that we haven't really covered, but also brought this with which to troll you. So this is an x86 handheld from 20 years ago, and it runs for 40 hours on 2 AA's. This is Zen5, Zen6, Zen7 power goals.
No, man, that's 2 AA batteries.
2 AA batteries.
This is where we want to get to, people.
8 megahertz.
This is where we want to get to.
That's maybe the problem.
But no, I mean, maybe we should have a couple of cores that can run 8 megahertz, for some, maybe. Yeah, for some background tasks.
So I use that to kind of, introduce the idea of, I've been trying to get my framework laptop to run for 16 hours, and I've gotten close. I've gotten it up to 12 with just the patches to the Linux kernel and everything else, and that is with a 7740 8-core and 32 gigabytes of memory.
Right.
That is very, very impressive. So with the new Zen5 stuff launching, you guys have doubled down on power management and everything else. Talk to me about, like, for my peanut gallery journey on power management, it's not really to do with like the core, but transitions, like those take a long time. Like I'll run a trace on an application, and there's a lot that goes into that, and I don't have any clue. Nobody appreciates it, so clue us in.
Right. So I think there was at one point in time there was an arms race on in terms of SoC states that you want to go into and how you would go into and ultimately save power, right?
Arms race, I like that.
Right, and so people kick out of those states more often than they like, and essentially the energy it takes to quiesce everything and go down to that state and come back up, net you might end up over engineering this and end up not getting the benefits that you want. But with Strix, we are increasing compute everywhere. We're going 50% more cores, 30% more graphics, 3x the NPU, all still in the same form factor, and we cannot let battery life drop. I mean, you cannot add anything without by taking battery life away. That's a cardinal sin. So more than just the IPs doing their bit on being efficient while they're active, idle, and quiescing them quickly, harmonizing them, and making sure that we can power gate them completely at the IP level, right, becomes really important. And that needs to happen automatically. Like you should not have to wait for a complete straight transition to get those states out. So individual IP hierarchical power gating is something that we have invested in. And this is a dynamic power management algorithm that looks at like a QoS based, a quality of service based, voltage frequency. And kind of says, hey, look, if someone's urgent and wants to do something, I'm going to ramp them up quickly, get them to where they are, and then bring them back and out. We understand the characteristics of our IPs and being able to gate them, and that should happen automatically. You don't have to go into the next level sleep state, if you will, by quiescing the world in order to get that savings. We can start managing to get some of those savings by just going IP by IP. So that's the first part. And then these chips are getting bigger. These chips are getting more powerful. So driving, it drives a larger fabric, both on the data and the control side, and it's sprawled all around the chip, right? So now we got to get more intelligent on segment-based, gating of those clocks, and say, hey, look, in this particular application, only a sub portion of the fabric is alive. The fabric runs on one clock, if you will, right? It's and the clock tree managed like that as you had small chips. But as you go larger, we're like, I need a subsection of this fabric only. Can I gate everything off? And this has to happen automatically. Really, the previously we gated these fabric clocks only when the entire system can be down, because the fabric goes everywhere. But now we said, pay attention to,
One of the interesting things that kind of came out in some of the material provided is that applications are not always the best judge of that. And some of the engineering that AMD's had to do reaches all the way into the application layer to say, okay, this application will use as much resources as you give it. It doesn't actually need that much. We should probably keep it in a power gated state.
Exactly right. So the moment you get a ping to say, hey, look, this is the kind of work that you need to do, understanding what, when and how often should we go into and come out of these states is really important to getting battery life. It's not about on paper, we saw the state, we made this new engineered state, which we never go into. We get no residency into. And to that effect, we also did what I call more improved retention techniques, because going into a state, like you said, is complicated. And you go to that state and you try to save state, and then you try to restore it. By then, you've been asked to go back into that state. And as you go to that state, you try to take all of the power down. There's DC losses on the platform. Net, you end up on the SoC. Seems like you were doing something intelligent. No net battery life gain. So we have been a little more disciplined in saying, hey, look, you can stay in an active state, but we will go into retention mode on a lot of things. So you can do a video playback now, which is what a lot of people commonly do, in a completely low power state, because we are actually gating a whole bunch of things. It looks like a lower state, but it gets there automatically by just monitoring activity and saying, that's not active, that's not active, that's not active. Gate all of that out. You all go into retention. Don't bother saving and restoring, because that's going to take a whole bunch of time, because you might have to jump out of this at any point in time. And then if you get more and more residency and you train yourself into saying, yeah, I think this really is down, you take that even lower to that state. So it's really about battery life on low utilization but high residency tasks that we have to optimize, because people are doing something. It's battery life, not in, people say idle all the time, but idle is when you go in and out of idle between keystrokes. We do that. And being able to gain as much power back in those periods of inactivity in a efficient manner, not by going into a different state, but by saying, can we put all of the IPs that are burning, both leakage and a dynamic power into a state where we don't have to burn excessive power going in and out of those states, at the same time end up with a net improvement in battery life. So you're going to see that with the Strix architecture. I think running lightly threaded workloads, you're going to see that gain come out of it, because we've designed it to get you more battery life, not out of the regular just keep it in idle and see how long it is, or standby power and so on. A lot of that really goes down to the platform as well, the components you use, how you build it. We're not a vertically integrated system. We're an open ecosystem. We have 200 designs, and we have a large AVL, like an approved vendor list. So people build designs whichever way we want. We are a fighter. We are coming up. So we cannot be making rules on these are the only choice components you can use. So those are limitations that we have. And sometimes, you end up with the systems like my AMD laptop. And it's not just the SoC.
It's a situation where it's like, oh, look at that. The CPU only uses 12 watts. Let's put in a 5-watt battery. It's like, oh.
Exactly. And so we don't control all of that. But at the end of the day, we take the blame. It is a Ryzen laptop at the end of the day. It's not a, XYZ component in.
That's what AMD Advantage is for.
That's right. And so we are advancing that. As you gain more traction, we'll be able to get a little more say in terms of, how we make these designs. And some of these high level design, like this top-notch designs that we're making, is going to start showing that.
Having both the Zen5 and the Zen5 C cores opens up a lot of possibilities too, because a lot of what you're describing with power gating and everything else, almost counterintuitively, most of the stuff that you're going to do on a laptop are going to live on those Zen5 C cores. But then when you need the performance, the performance cores can light up and you're good to go.
Absolutely. And I think it is about that. Once you understand the capabilities of the classic and the compact, it becomes clear what you want to use each of them for. For example, if you're running like a Teams application where it is constant, it's running, probably stay on Teams longer than I should, but it is going to get full residency to your compact cores. But while they are running, you want to open up a browser or an application that requires that responsiveness, that bursty performance, it's going to get scheduled on the classic. And it's going to have its own context, because it's going to be on its own core complex. So the caches are not getting muddied. They are two independent programs that are intended to run in two different enclosures, if you will. And once the browser is done, you get that responsiveness from those cores. It's burst. It goes back to sleep, and your Teams continues running in the background, right? So the goal was to elevate the user experience without taking away, anything in terms of efficiency, but just adding on to say, hey, look, we've got the best of both worlds, right?
Yeah, there's also a power aspect for PCIe as well, like NVMe, like power gating the NVMe. You can save a lot of power there too.
We can, and again, there are choices that our competitors have made around advancing storage in terms of speeds on NVMe's, right, or on our PCIe lanes going forward. You can see that, why aren't we going to PCIe Gen 5? I mean, you bring up an excellent point, right? It's an end to a means. 5 is greater than 4. We get it. It's higher bandwidth. It's there in our desktop parts. In fact, if you want to make a mobile gaming system, you can use one of our FL platforms, the range products, and you can build a PCIe Gen 5 based laptop if you want it. But for our mainstream laptops where power efficiency is key, we're sticking with PCIe Gen 4 for another generation, right? I mean, we have that capability in our arsenal. You can see it in our other products. We're not bringing it into mobile because it doesn't need it. I think the bandwidth to storage right now yet does not really move any meaningful user experience other than some benchmarks. If you're using nonlinear editing, if you're that kind of a user, you're going to disk and bringing gobs of data over. Sure, Gen 5 would be great, but for 98% of the folks that use a laptop, I think Gen 4 is good. So we're not going after speeds and feeds. We're being power conscious.
You know what else is faster than NVMe? RAM. 48, 96 gigs of RAM, not a problem.
That's right. So I think it starts with that vision. Like, what do we think is going to move our user? We think it's better performance. It's what you said, battery life all day, and being able to do and to have that system be something that doesn't hold you back. You want more compute? Plug it into the wall. If there is a delta between AC and DC performance, and it's for a reason, right? I mean, some people use our laptops as replacement, desktop replacement. They want that compute. The 12 cores can still chug along, right, and give you that performance if you want it, but they can hum at 15 watts and give you that power efficient operation as well.
Giving you 16 hours of battery life and an OLED screen is basically all anybody wants.
That's right. But I think as time progresses, people would want to do more during that. Like, that 16 hours might involve 8 hours of Teams with 3FX running. And so you have to get and collaborative work that you'd be doing with a lot of people. I mean, so the NPU comes in handy. Those tasks, not only do they have to get done, they have to be done efficiently. So the days of idle battery life is going. I think, like you said, it's between 12 and 16 hours of battery life that you want, but what you intend to do during those 12 hours is evolving, it's changing, and the accelerators we're putting in, we're not shying away from putting more compute in. I hope that comes through, right? We're not saying, it's all about battery, let's try to go smaller and narrower and more efficient. We're putting in more cores, more graphics, more NPU, more than the standard that's needed for Copilot. They said 40, we're giving you 50. Like, we're always pushing the boundary, and I think building the hardware first. I think software, the ecosystem in terms of experiences and ISVs will come around it, and that's always been the case. We broke the mold on desktop going to 8 cores when 2 or 4 was supposed to be enough, and
now 12
with Threadripper, and now you have 12 on your mobile platform that has a 15-watt TDP. So. Yeah. I think we'll continue. That's in our DNA. We'll continue doing that.
So thank you for joining me, Mehesh. This is very awesome. Is there anything else you want to shine a light on in the SoC that doesn't normally get attention? Because C states are exciting. That's the thesis of this part.
No, and it is, and I think the attention to detail that we've given to power efficiency. I just want to underline that a little more. Like, when we added 50% more cores, we had to innovate to bring compact cores in to balance that. It didn't come for free. When we added 33% more graphics, that came in with all the features that Mark just spoke about at Tech Day, where performance per bit, performance per watt enhancements, as well as memory management. So we go to memory less often and burn less power. And the NPU, right? When we said accelerator, 2x the efficiency and 3x the peak tops. All of that, again, is keeping efficiency in mind, squeezing all that in. Even the NPU design, everybody now talks about the 40 tops NPU, and everybody has it. Each design is unique. Each design is different. Ours, like we talked about it, is column-based. It is meant to be scalable. As we get more and more concurrent applications to start running, you will see our NPU shine more. We have the pedigree of designing NPUs from our Xilinx days. I mean, we have done this a few times, and we know what we think is the most configurable, ready for the future, NPU design that we think is the software will catch up as we try to add more and more experiences in, and the nature of our architecture will lend itself well into it. So I think on the forefront of having the best IP on CPU, GPU, and NPU is important to us, but blending it all in, keeping power in mind, I think that's been the feat. That's been the way of, that's the miracle I think that we've put together here in the Strix Point SoC.
And we did get a quick run through with Vamsi Bapana about AI and AMD's AI approach in the NPU. And they had some slides that they shared with us at Tech Day as to what it means for the third generation of Ryzen AI. The AMD XDNA AI engine, like Mehesh was saying, is kind of a grid. You can partition it however you want. And this is maybe an innovative feature because you can say, okay, this part is going to be reserved for Microsoft's AI function in Windows, but this other third of it or this quarter of it could go toward your own runtime or doing video decode or doing something else outside of the Microsoft ecosystem. And certainly partners of AMD like Lenovo and HP have their own ideas of what they're going to run on AMD's XDNA engine outside of the 40 tops or whatever that Microsoft reserves for the operating system. XDNA 2 here ends up being 32 AI engine tiles and up to 50 NPU tops, which is 10 trillion operations per second above the minimum that Microsoft has set for Windows AI experiences. So over the previous generation, that's 5 times the compute capacity and twice the power efficiency. So not a bad achievement moving into ZEN5 and the ZEN5 mobile SoC. And if you're thinking, gosh, I would love to have this on the I/O die on Ryzen desktop, maybe in a future generation, but you can get a lot of this done with your GPU instead in a desktop context. The reason this doesn't make sense for mobile is strictly down to power. They convert things that could be done with a purely software experience into something that is done with hardware transistors because overall that uses dramatically less power. A little bit less flexibility, but if you know you're going to be running certain types of AI applications, it makes sense to go this route on mobile. And the demos that AMD showed were Stable Diffusion XL Turbo, which ran quite competently. And they also ran a couple of demos where you run the AI locally and you feed it documents, so you don't have anything going to the cloud. And then you can ask the AI questions about the documents that you've fed it. And it's nice having that peace of mind that the AI is not sending your documents to the cloud for processing, because Lord knows what happens to them once they leave your machine. And to be clear, with the Unified Onyx EP, you just download models from Hugging Face. These are the models that you've come to know and love. There is some special sauce, some interesting things happening under the hood to do with how AMD is representing the data types. It's almost 16-bit accuracy, but it runs like it's 8-bit, and it turns out it's because it's 9-bit. It's mostly 8-bit, and then there's a shared exponent for this data type, which is interesting. It's interesting to see how that's going to play out in the market, but this is drop-in compatibility, so like Llama 2 7 billion, and it's going to be 99.9% as accurate as standard 16-bit floating point. So impressive. Now, what Mehesh was talking about with the SoC is that there's an NPU on the SoC on mobile ZEN5. And the reason there needs to be an NPU on mobile, when you don't see that on desktop, is because you need efficient AI. You need a way to run AI efficiently that doesn't have your GPU blasting. It's like playing a game. You play a game with your GPU and your system will be dead in an hour or two. You don't want that if you're running AI tasks in the background. So the NPU. Now, something that's been top of mind for me is what is the NPU developer experience? And I'm fortunate because I was able to do an interview with AMD personnel at Computex about AI and everything like that. I'm just now getting that done, partly because of the Onyx runtime and partly because I wanted to take some of those things for a spin. And so I've got that coming up in a video. Stay tuned for that. But yeah, the Onyx and the NPU architecture, the direction that AMD is going is not really the same as what Intel is doing with Lunar Lake and their WDDM approach. And so it's going to be interesting to see which one of these wins in the market. The reality with AI programming right now on mobile is that there needs to be a killer application. And the reality is that developers, at least small-time developers or small studios that are working on these kinds of things, if they come up with a killer application, it is probably going to be GPU first. And then it will be ported to a platform-specific NPU, Intel, AMD, maybe for mobile phones, whatever they have, whatever Apple's doing, whatever Samsung is doing, whatever Qualcomm is doing with their thing. But the killer application has to exist first. But it's a little bit of a chicken and egg problem where we're at right now. It's like AI is going to be big,
probably for the individual. It's certainly been big for business, but how is that actually going to translate into usable applications for the end user? That remains to be seen. But if you build it, they will come. I don't know. We're going to have to stay tuned for a future video. I'm Wendell, Level 1. I'm signing out. You can find me in the Level 1 forums. Look for that on Patreon and Floatplane and pretty soon on the channel. All right, I'm signing out, and I'll see you in the forum.